So as I mentioned earlier, today we're fortunate enough to have Dr. Andrew Thomas presenting his overview of machine learning for engineering and analytics. By way of introduction, Dr. Andrew Thomas is a principal engineer at Energy Queensland. In his career to date, Andrew's worked with Energy Queensland and its prior organisations for more than 10 years, and previously worked as a lecturer at the University of Queensland. In his nominal role, Andrew is responsible for determining the impact of future load and DER scenarios on Energy Queensland's network, and for finding solutions to those emerging constraints. In his personal time, Andrew is the founder of the blog Adventures in Machine Learning, well worth a Google or a quick search on the internet, and the author of the book Coding the Deep Learning Revolution. He also enjoys creating machine learning solutions to problems and teaching others about machine learning. So all topics extremely relevant to today's webinar. And again, a bit of a plug to some of that work that Andrew's done. His research interests include facilitating least regrets decision-making in the distribution network, facilitating increased levels of DER, and using machine learning, optimization techniques, and automation to improve planning outcomes and efficiency. So has a knowledge base extremely relevant to this area and is very learned in this area, and really looking forward to hearing more of his presentation. So with that, Andrew, I'll hand it over to you, mate, if you want to screen share, and you can take control from me and take it away.
No worries. Thanks, Matt. Let us know if you can see that.
Yeah, so that's come up with the PowerPoint window here. Yep. And now in presentation mode.
Awesome.
Okay, so I'm just going to put my end on mute. Just a reminder again, if you want to ask questions, please unmute yourself. If you're not asking questions, please keep yourself on mute. And that chat facility is there if you want to note something down but don't feel confident speaking up. All right, Doc, thanks very much for that.
No worries, Matt. Yeah, hello everyone. Thanks for coming along. So yeah, today I'm going to talk about machine learning, and in particular focused on its applications in the areas of engineering analytics. But it's going to be sort of a somewhat lightning overview. Machine learning is quite a big topic, and too much to cover, within an hour or so, but I hope to cover some of probably the more cutting edge techniques that are around these days, and in the process of doing that, cover some of the more relevant components of machine learning and things you have to look out for if you're going into if you want to start learning more about it. And as Matt said, feel free to jump in at any time with questions. If I'm covering something too quickly or not explaining things properly, I prefer more interactive presentations rather than me just droning on for an hour or so. So yeah, feel free. So just to kick off though, so what is machine learning? Well, informally, it's basically, informally, it's the ability of machines, computers, robots, etc., to learn to perform tasks at a level approaching or surpassing the ability of human beings. They're really, machine learning algorithms are really just mathematical models which can sort of adapt based on some data supplied and a goal that a human, gives the algorithm. And there's three main types of machine learning. The first is supervised learning, and that's where you basically hold the hand of the algorithm and supply it in both input and output data. So in the case of a classification task, say you supply some images to a certain machine learning algorithm, and then you also give it a designation of what class that image belongs to. So, if it's got a picture of a cat or a dog or a horse in it, you give the machine learning algorithm a label to say this image belongs to this type of class or category. And so then it starts to learn, if it's working well, it starts to learn the relationships between those shapes in that image and those classes, for instance. And over time, as you train it, it'll get better and better. And then the idea is at the end, once it's trained as good as it can be, you then can put in a new image and it should be able to automatically detect whether, there's. That's a classification supervised learning task. Regression is somewhat similar, but instead of a discrete class that we're trying to predict, like whether this image has X, Y, or Z in it, it's usually predicting some sort of real value. So the example I give there is, what's the load going to be on substation X at 2 p.m. in 5 days' time? So in this case, you train the model on historical load data and say temperature and what day of the week it is and that type of thing. And then at the end, you'd hope it would be able to predict the load, at some point in the future. Unsupervised learning is it's really probably the ultimate goal of sort of artificial intelligence and machine learning. And the idea is that you provide little to no supervision of the machine learning task. And one good example of unsupervised learning is clustering, which you may be familiar with, where you've got some sort of mathematical algorithm and it's trying to understand what the underlying structure of the data is. And then finally, reinforcement learning. Basically, it's a kind of a form of supervised learning, but we're trying to train an artificial agent to operate in an environment. And mostly that's so the reinforcement learning techniques are mostly tested these days on playing video games. So you get an agent and you teach it how to play, Mario Kart well or some other game. Which may not sound like it's very relevant, but you can actually you can take any kind of real world task and formulate it as a game with rewards and benefits and so on, and train an agent to perform well in those types of environments. So today, I'm not going to talk about unsupervised learning, but I am going to talk about supervised learning and at the end touch on reinforcement learning. So there's a lot of hype around machine learning and AI. Now, is it correct? It's one of those questions with the way technology is going, at an increasing at an exponential type rate. It's really a difficult question to answer. But you can see a couple of those quotes here. So you've got the Google CEO saying that it's more profound than electricity or fire. You've got this guy, Dale, I won't try to pronounce his name, at the Artificial Intelligence Lab in Sweden, where they're saying that AIs will colonize and transform the entire cosmos, and they'll make it intelligent. So that's a fairly big claim. Another professor here is saying most jobs will be done by robots within 30 years, and about half the AI community believes computers will be as smart as humans by 2040. So big claims. Are they right? Who knows, really? That's my view. Certainly AI is going to be a significant part of our lives in the future, but to what level will it be able to achieve general intelligence and all that sort of thing? Who knows, really? Here's Gartner's, what's it called, hype curve, or I think something like that. It's a bit older, it's July 2015, but it's showing that machine learning is kind of at the peak hype. I did pick up, I did look at an earlier one yesterday, sorry, a more recent update of this graph yesterday, and it showed that machine learning was down this curve a little bit more. So yes, still very hyped up. When it gets to this so-called plateau of activity, who knows? But it does have a lot of promise. I think that's undisputed. The sort of popular conception of AI is the Terminator, but the reality is at the moment, so this is an automated captioning machine learning algorithm. And it's saying that this is a boy with a baseball bat. So, we're a way off Terminator levels of intelligence. Okay, so I've purposely made this presentation be quite maths light, but there are some, basic type of maths ideas that we have to think about with machine learning. So generally, you can think of machine learning as kind of a black box with a certain set of parameters and certain functions that relate to those parameters. And the idea is we give this is a supervised learning case, we give the black box some input data and it produces some sort of output data. And we want it to learn why. So say to give us, we'll say we give this an image of with a cat in it, we want it to say output cat, or the label corresponding to cat. And we give it that type of image. So we want it to produce y, but in actuality, it produces this y hat, which is an estimate of y. And so we want to vary these parameters inside this black box such that the difference between y and the estimate of y becomes as small as possible. So different machine learning methods have different model structures that interact with these parameters. So for instance, neural networks have a certain type of parameters called weights, and other machine learning algorithms have different parameters, but they've all got parameters that can be changed because that's the learning component. Now, the training data is actually a series of XY pairs. So we input a certain X, and we say we give it a certain Y, and we want to move the output of the machine learning algorithm towards that Y. And each XY pair is an opportunity to update these parameters. So usually, for most, I would say most machine learning algorithms, they rely on some form of gradient descent optimization to arrive at those optimal parameters. So say we input certain X value input to the algorithm and it produces an estimate. We then, if you just look at this graph here on the right, it will produce a Y that's up here somewhere, and which is some way off what the truth or the value we want, which is Y. Now this is called a loss function, this blue line. Obviously this is just a stylized loss function. But the form of this here, Y minus Y hat squared, is called the mean squared error type of loss function. So back to what I was saying, so we input a certain X value, it produces an estimate of Y hat. We then calculate the loss function at that point for those parameters, so theta naught. And then we take a gradient at that point of the loss function with respect to those parameters, and then we take a step. Now we're at parameters theta 1. And then we put another training pairs in. Again, we take the gradient and take another step, and the idea is for it to converge to some sort of minimum. Now, that minimum should never, in any realistic machine learning model or scenario, that should never get to zero because there's always going to be noise involved with your data set. So, but the idea is to get it to some low value, ideally what's called the global minimum value of your loss function. But in reality, they usually fall into what's called local minima, which isn't your absolute best value of your loss function, but it's good enough. Usually, that's how we do things. So, to provide a pretty simple example, I'm just going to use a simple linear regression problem. So, basically, this is a simple line fitting method where we have some noisy data with a trend, and we want to try to fit the line of best fit through that data. So I'm sure you're all familiar with this type of problem. You could say that this is a machine learning problem. It's probably a bit of a stretch, but the basic components are all there. The parameters that we're going to try to vary in this example is your gradient term, so M, and your intercept term, which is C. And so that's what your parameters are in this simple linear regression example. Now I'm going to try to run code here, so just bear with me. I assume you can see that. So this is a Jupyter notebook. This is running Python. Now, don't worry too much about the details if you don't know Python or NumPy or any of that, TensorFlow or any of that sort of thing. This is just to give you a bit of an overview, so don't worry too much about the details. So here, what I'm doing in this block of code here, I'm setting up an X array where it varies, basically creates an array of values between 0 and 10. I then set the true values of the M and the C parameters, so a gradient of 2 and an intercept term of 1. I pack that into a parameters array, and then I create the true Y, basically. So this is just the multiplication between the X array and the parameters, and that gives us this nice red line. And then I'm adding some random noise to that nice red line to produce all of this noisy data. Just run this so that it will actually work. So every time I run this, it will actually change the noise because it is truly randomized. So you can see that those blue dots change at each time. Anyway, I then do something where I convert these variables to what's called tensors. Now, tensors are basically just multi-dimensional arrays where the dimensions be whatever many dimensions you like. Tensors are used in this package called TensorFlow, which is probably the predominant Python library to do deep learning, which is something I'll talk about later. But I'm using it in this case just so that I have an optimizer that I can easily use to solve this problem. The next I define the loss function. So if you remember, that's basically, I'm defining this here, the loss function. That's what we're going to optimize to reduce it to as low as possible. So you can see here that the loss is calculated in this function where we take the actual true values minus the predicted values from the linear regression here, using the current weight values, and we square that and take the mean of it, and that produces the loss. Now, at this point, I set up an optimizer. So I'm using, in this case, what's called an atom optimizer, and that's a form of gradient descent optimization. And then we enter into a iterative loop, where at each point, at each iteration in that loop, we input X data, the noisy Y data, and the current parameter values, calculate the loss. But while we're doing that, we capture the gradient of the loss with respect to the weights, the parameters. And then we apply those gradients to the optimizer, and hopefully the idea is that the loss will decrease until it plateaus at a certain point, and that's the point of your best, the line of your best fit. So let's just run that now, and we'll just see. Here it is, it's just going along. Hopefully that's not buffering or anything. You can see that the loss value has basically stagnated at this point, so it actually converged relatively quickly. I'll just stop it there. And let's have a look at the W. So these are the parameters. So the true values, true parameters, is M should be 2 and C should be 1. Now, if you look at the actual parameters that were arrived at, M is 2.5, C is 2. So the noise is throwing off the estimate here. So if we plot this out, you can see that the noise has created basically an offset in the estimate of the actual true line. So that's what I'm saying. If you've got any noise in your problem, you're not going to find the exact solution that represents the true process that's generated that data. You're only going to find an estimate of it. But in this case, you know, it's not too bad. Does that make sense? Has anybody got any questions at this point? Take silence as no.
Android, is Matt here. Sorry, a bit slow on the mute button. So with that, I guess you can extend that fairly quickly by doing things other than linear regression. So like using a quadratic function or something like that.
Yeah, exactly. Exactly, yes. Yep.
But like, how much of that whole process goes into like understanding your data before you try and fit it, like, and knowing that that should be a linear, or do you just try a bunch of different functions? And in cases like this, I mean, I know this is a simple manufactured example, but when you're looking at your data, how much your effort is in like actually doing the computation behind the machine learning or the regression, and how much of it is understanding your data and what you're trying to solve?
Yeah, in reality, in this, it's probably the major component, and I'm probably writing roughshod over that component in this presentation and focusing mostly on the machine learning aspect. But it's a good point you raise. A lot of perhaps most of the time spent in doing a machine learning task is getting your data into a good format, getting rid of any rubbish that you know is actual rubbish data that you know is truly rubbish data, cleaning it up and so forth. And then, yeah, you should really be running various sort of diagnostic tests over your data to see what the distributions are, and so forth, to come up with what you think is actually the underlying process that is generating the data. Because, yeah, as you said, ideally you should be trying to match some sort of algorithm with the data, that the relationship that the data is showing, just by eyeballing it, if you like. Does that make sense? So, yeah, I'm basically agreeing that.
Yeah, okay. No, that does, and definitely, I guess it becomes hard as you get more and more data points, and it's not just a two-dimensional thing anymore.
Yeah, that's right. Yeah. Any
so that's an art in itself, really, is it?
That is an art. Yeah, definitely.
Okay, thanks for that.
No worries. I'll just say that just at this point too. While it is an art, that sort of art is to some extent falling away, in that they're starting to produce these what's called auto ML, or auto machine learning, which is basically it automatically goes. There's code libraries out there now that will automatically try all these different parameters for you and come up with the best type of learning model to use. But yeah, that's odd.
Actually, Andrew, I did have another quick one, but it was back to a slide you had previously around the hype curve and where machine learning is on that. Do you think we're hitting a point where people are like the next progression is the trough of disillusion? Do you think we're getting to that point with machine learning? Like, it is, and this is taking a step back from the technical discussion you just run through there, but it is a term, and like AI, machine learning, all that is fairly hyped. Do you think we're hitting a point where it is under delivering on people's expectations, or people are still really interested in it and it's still got that bit of an aura around it?
I think no, I don't think it is hitting this. And to be honest, I'm not sure if it is still sitting. I mean, it's definitely hyped, but I think it is producing. Like, you know, if you go to somewhere like Facebook or Google or what have you, their use of machine learning would be increasing rapidly in their production system. So to say it's sort of sitting down here somewhere where it's kind of not producing much, I don't think that's right. In my view, it's sort of sitting up here somewhere, but where it's actually, you know, delivering in certain areas. I would say that artificial intelligence, you know, the idea of general artificial intelligence, where, you know, you have algorithms that are truly exhibiting signs of intelligence, I think that is probably way overhyped, and it's a long way off, even if it's even possible. That's where I think the hype is not, you know, is a long way off actually producing anything. Machine learning itself, as in terms of actually solving problems, it's definitely at that point. You know, it's not just a hype that's doing, everybody's talking about it, but it's not actually doing much. It is definitely being used a lot. So.
Yeah, okay, that's a fair point. When I saw that chart, I thought it sort of suggests that at some point that we expect a bit of a realization that maybe it's not quite as impressive. But yeah, exactly what you're saying. There's organisations like Google, like Facebook, and a lot of other image processing stuff that seems to be quite impressive and fully functional. So it seems like we'd, like you said, be a bit beyond that from a machine learning perspective.
That's my opinion, yeah.
Yeah, sorry, thanks for that.
No worries, no, it's good. Okay, so a perennial problem for machine learning is something called overfitting. So just building on that simple model, overfitting is basically it's when a model fits the data that it's trained on really well, but it doesn't perform well for data it hasn't seen before. So basically, you're making the model more complicated, or more complex, I should say, than the data you have to train that, or the actual underlying mechanism that's producing that data. So considering this case, you've got a simple model here, mx plus c, which we've already done. And the loss for this case and this distribution of noise, the loss is 13.8 after the fitting process. Okay. Now, you can actually create a more complex model where you introduce all these polynomial terms, and you get a training loss, so a loss on the actual data that you're training these parameters on, lower than the simple model. And so, you know, if naive, you would say, oh, well, that's a better model. But in reality, if you then go to and you give the algorithm data it hasn't seen before, so which is called test data, the model diverges because of all those polynomial terms. And so you can see here, you know, the simple model, the test loss is a little bit higher than the training loss, but it's nothing compared to this complex. So whenever you're doing machine learning, you must basically split your data into a training and a test set at a minimum. So usually, you know, you say you've got 1,000 points, you'd split 800 of those points and say that's your training set, and then 200 of those points remaining will be set that you actually test the trained model on to make sure it's working as you'd expect it to. All right, so that's kind of an introduction using a very simple machine learning method. And if you want to call it even machine learning, it's more of a statistical method, but anyway. I'm going to introduce two state-of-the-art high-performance machine learning methodologies, and these are called ensemble methods. Included within those ensemble methods is a methods called random forest gradient boosting and XGBoost. So I'm going to give you an introduction to those, and also then neural networks and deep learning, which is the hype within the hype of machine learning is deep learning. So what ensemble methods are, so just addressing that first one, set of models first. Ensemble methods use collections of weaker machine learning models and then gather them up to create a kind of super estimator. So one of the problems with machine learning models is, or training machine learning algorithms, is that you tend to need, one, a lot of data, and also it can take a long time when you're using lots of data to train your model. So the idea behind these ensemble models is that you use weaker machine learning methods, which are easy to train, and then you sort of gather them all up and use and create this super model, which is an ensemble of all these weaker machine learning methods. So usually in ensemble methods, the weaker machine learning method used is called decision trees. Now, there are many useful Python libraries to construct these decision trees and ensemble methods. And one of the most useful of these is called scikit-learn. If you want to get into machine learning, that's a really good place to start, is using that scikit-learn library in Python. It's good just to start playing. It's really easy to create models and just start playing around with them. So it's a good place to start if you haven't got into machine learning before. You want to have a go. But basically, the idea about these ensemble methods is that they're fast to build, to train, and quite powerful. So decision trees are a way of performing classification or regression based on a hierarchical series of if statements, which cut up the data. So in this case, here we've got a very simple decision tree with a depth of 1. And again, we're using just this linear problem. You can see here we've got our linear red slope here, some noise around it. The green here is that depth 1 decision tree fit to this data. So in this case, it says, okay, if the X value is less than 3.5, which is about this point, output 3.3. If it's greater than 3.5, output 14.5, and that's the fit. Kind of pretty easy and straightforward. And then if you make the depth of the tree larger, so in this case we've got 2 layers, or the depth of 2, it splits it further. So if it's less than 3.5, it then does another split. If it's less than 1, it outputs minus 2.8. Within that split, if it's greater than 1, it outputs 4.3, and you can see here it just generates this type of estimate. Now, the problem with decision trees on their own is that they overfit badly if the maximum depth is not restricted. In this case, you can see here that I've just fit here, in this case, a decision tree with no restriction on its maximum depth, and it's just gone after every single point. It's gone after the noise in the model, basically. That's what overfitting is it starts going after the noise of the model, and it's not trying to represent the underlying mechanism that produce the data. So that's the training set. And then if you go to the test set, so going beyond 10 here, so 20, the linear model is far superior, and the decision tree basically just gives up at this point and just outputs a flat of 2 or something like that value. So the solution to this overfitting problem of decision trees is the ensemble methods. So first version of these ensemble methods was called bagging, and what that does is it trains multiple decision trees, so tens to 100, hundreds, but only on a certain percentage of the data. So for instance, each tree is only trained on 50% of the training data, and that's randomly selected for each tree. So you can see that it's kind of doing its own test training data split up, and each tree is only on a certain percentage of that data, so it reduces the chance of overfitting. And then the output is you take the average prediction of all these trained trees. So you've got 100 simple decision trees trained on a certain percentage of the training data, and then you take the average of the output of all these trained trees, and that's your prediction. Oh, that's just the algorithm there, but it's basically just what I said. Now, random forest is basically the same as the bagging method, but it uses a random subset of the features used to train each of the trees. So this is relevant for when we have multiple input features for the X input data. So what am I saying there? So, in these cases, we've only got a one input feature, which is the X value, so a single dimension. But in any through machine learning problem, you're going to have potentially hundreds of input features, tens to hundreds of input features. If you're doing something like load forecasting, which is just an example here, your input features might be the hour of the day, the temperature, the humidity, whether it's a weekday or a weekend, the number of customers on whatever network element you're trying to forecast, etc. In this case, you have 5 features. So random forest takes a random subset of your data to train each tree, but also a random subset of the total number of features. It might only use, say, one tree might only use hour of the day, temperature and humidity. Another one might use whether it's a weekday or weekend and the number of customers and so forth. So this is all just to give to purposefully reduce the complexity of the model, basically, so that it doesn't, to try to prevent that overfitting. So you can see here, the green is the random forest model. So again, it is still going after the noise. So it is still overfitting, but something to remember here is that this is random forest. This type of problem is a massive overkill. So we should expect, a complex model like this to overfit a simple. But one other thing to realize is on the left-hand side here, we've got the training data set, and on the right-hand side is the test data set. And you'll notice that, again, once we get samples or data outside of the domain which the model's been trained on, it doesn't perform very well. So that's one thing about ensembles, is that or decision trees, is that they're not great for predictions out of samples, so data which is significantly different from what it has seen before. You can fix that. So you can build in ensembles of, rather than having a decision tree as your base estimator, you can actually just create an ensemble of simple linear regression models. So in this case, you could use hundreds of linear regression models instead of decision trees, which you can do in scikit-learn. And this is the result when you do that. So much better outcome. But in saying this, this is really just to generate, this is just to demonstrate random forest methodology. And this is definitely an overkill for this type of problem. So I hope I haven't lost anyone there. So let's use it for a more realistic example. So here I'm going to use the random forest machine learning algorithm to do feeder forecasting. This is a real feeder from EQL's network. Y here is the KVA, and X is just a year's worth of data, so a 30-minute KVA recordings for that feeder. Now, the input data to this model is, in this example, the hour of the day of the year, minimum temperature for that day, the maximum temperature for that day, and the day of the week. That's 5 features. Y is the feeder KVA data. Total number of data points is 17,000 odd. And in this case, I've used a train test split of 90% training data and 10%. Now, if I just use the default random forest estimator or model out of scikit-learn with an uncontrolled tree depth, you can see here that the training R-squared value is 0.99 and the test R-squared value is 0.68.
Katrina, Johnson from Line Standards, how are you? Yeah, I just got a question, urgent query from the supplier for a tender, a secondary switcher tender. It's about to close on Friday. I just want to ask you, because I checked with Matt Pope about our radios, mesh radios. So he was saying that we can't pre-issue them, so we're to the contractor. So we're currently.
Yeah, sorry, Doc.
No worries.
I thought that was a genuine question for a while. That's why I was a bit slow to jump in.
It's all good. So yeah, in this, so just to recap, so R-squared values, they're a mechanism of how good a fit is between two different curves or whatever, between the data and the prediction. So the perfect fit, you get an R-squared of 1. A fit where there's no correlation between the data and the model, you get an R-squared value of 0. And in the opposite direction, if it's correlated negatively, you get a negative value. So, so in this case, you can see that training R-squared value is really high, so 0.99. Test R-squared value is 0.68, so not as good. The reason that's going on, that is because the model's overfitting. If you look here, we've got, I purposefully left in some noise in this data. So you've got a couple of outages and some switching peaks where this feeder is being used to supply another feeder, adjacent feeder, say. Now you can see here, the red is the the model prediction, and the blue, which is sort of hiding behind the red, is the actual data. So you can see that the model's gone after the noise, which is a telltale sign that it's not really predicting the underlying model that's generating the data. It's just going after the noise, so it's overfitting. So what do we do in this instance? You need to do something that's called hyperparameter tuning. Now, sounds a bit complicated, but you know how I was saying before that every machine learning algorithm has parameters that need to be trained to predict the data. There's also another set of parameters called hyperparameters, which sort of describe the model itself. So in this case, let me just go to the next slide. In this case, for random forests, max tree depth is a hyperparameter that you can change. So if we go back to the decision trees, so remember random forests are usually decision trees. So this depth, the maximum depth of the decision trees that are in the random forest can be controlled. So you can say we don't want it to go any deeper than 7 or 8 or 9 or something like that. So in this case, in this example, I've restricted the maximum tree depth to 7. And that produces a much better outcome. So the training R squared is lower, so 0.87 input instead of 0.99. The test R squared value has gone up from 0.8 to 0.82, which is much better. So in reality, if you're getting training R squared values of greater than 0.9 or something like that in a regression problem, there's a fair chance you're overfitting, because it's really quite hard to get correlations that good when you've got noise in your data. So you can see here the training data here. Again, it's not as perfect as if you like as it is in this case on the training data, but you can see it's not going after those noisy points. It's just modeling the underlying trend of the data. And then you can compare that with the test set. It's not perfect, but you shouldn't expect it to be. It's much better than what it was. So that's why you need to look at these hyperparameters. As I was saying, most machine learning models, or actually that should probably be all machine learning models, have a host of what's called hyperparameters, and these often need to be tuned as well. So in this case, I've got a table here of the max depth hyperparameter, where I've changed its value and compared and calculated the training R squared value and the test R squared value. And you can see that the best value of that hyperparameter is 7 in this case. It's because it has the highest test score. Now, because of the fact that you've got these hyperparameters which you need to tune, really you should split your data into 3 parts. So not just your training and test split, but your training, you should have a training data set, a validation data set, and a test data set. The validation data set is where you do this hyperparameter tuning. So you'll train it on your training set, the model, with a certain hyperparameter value, and you'll see how good that is on the validation data set, and then you'll change the hyperparameter value to another level, and then again compare that to the validation data set. And that validation data set is what you'll use to select what you think is the best hyperparameter set of hyperparameters for that model. The reason why we don't just use the test set to do that is because you could actually manually overfit your model. So, if you just have a certain amount of training data, and then you're using the test set data to come up with the best values of those hyperparameters, you could be basically just manually tuning your model, and if you give it data it hasn't seen before, it could perform badly on that data, and you wouldn't know because you haven't kept that test set aside. I hope that makes sense. Something called
that, Andrew, Matt here. Just again, I'm guessing. So for that random forest example, we're tuning one parameter, but I'm guessing with the hyperparameters, you could be tuning multiple at any one time.
Yep.
Like it's not just a one at a time sort of scenario. You have potentially models where you could have 2 or 3 hyperparameters that you're working with.
Yeah, there's usually, definitely. There's usually more than one. Can be a handful or more. So in that case, you really want to do something called cross-validation. And that's a method to kind of not automatically, but you set up a big loop where you go through all these different combinations of hyperparameters. You'll set it off overnight or something to run. And hopefully you'll come back in the morning and it's finished, because it'll take a while, depending on your data set and all the rest. But and hopefully you've arrived at an optimal hyperparameter configuration.
Yeah, okay.
And then you can then use that on your test set, and then you know that the test set's kind of pure, and you know exactly how well your models.
Yeah. So it sounds like this is a fair level more complex than just doing like a decision tree sort of model in terms of computational complexity. Yeah. It's just a number of different variables that you're now starting to process that increases the complexity.
That's right. Yeah. Yeah. You're training the model over and over and over again with different models.
Yeah.
So that's just going to speed it up. Yeah. No worries.
Hey, Doc or Andrew, it's Adrian here.
Yeah.
Just a quick question. With the test data set that you had there, or the examples data, it was pretty obvious to see where the outliers were and understand that the algorithm was chasing them. Is it, I guess, advantageous when you have data sets to be able to understand that prior to going through this process, or can, for data sets where it's harder to determine what actually is an outlier and what's a genuine piece of data, can this method still be just as effective?
Yeah, the only thing, ideally you'd want to be able to get rid of all those outliers prior to any machine learning method, but in reality, as you said, in some cases that's not possible because you don't actually know what's the outlier and what isn't. If you don't actually know that it's an outlier, you're kind of stuck with regards to whether you can understand whether the model is actually chasing after values that are just basically noise. I guess that's what the test set is for. The more data you have, the more likely you're going to be able to pick out those sorts of issues, if you know what I mean? Because you're covering more of the possible outcomes of the
Yep. Sounds good. Yeah. Thanks, mate.
Yeah, you're right. I'm taking a little while here, so I might speed up a little bit, but basically gradient boosting is another ensemble method, and this is sort of the best ensemble method out at the moment. I don't know if any of you have heard of the online machine learning competition website called CIGRE. Gradient boosting algorithms are often in the top leaderboard of those competitions. But in any case, instead of each tree trying to predict the full training data or a certain percentage of it, what gradient boosting does is it fits a weak estimator. So, it starts off with a single decision tree, FM. But the next tree doesn't try to fit Y, but it tries to fit the difference between Y and the output of that first decision tree, so the residual. And it just keeps doing that over and over again. So each tree isn't trying to do the whole Y data, but it's just trying to fit the difference, the unexplained variance of the data, if you like. Now, the good thing about this is it allows various loss functions to be used. So as I said before, there's the mean squared error loss function, but you can also use something called quantile loss function. And what that does is instead of trying to predict the mean of the data, you can predict, say, the 90th percentile or the 95th percentile, conversely the 5th or 10th percentile of the data. And that gives you basically a kind of uncertainty estimate of your predictions. So if you go here, this is an example of that. In this case, I've got a gradient boosting with a max depth of 4 as a hyperparameter. Training R squared is 0.94 and the test R squared is 0.84, so pretty good. And so you can see here that the red is the mean output. The blue is the actual load data, but behind that you can see a light blue shading, which is the uncertainty bounds of the prediction. So that can be really handy if you're doing some sort of probabilistic simulation of Monte Carlo or that type of thing. The XGBoost and Light GBM are basically high performance implementations of gradient boosting, and they're the sort of go-to machine learning models that most people use before they go to deep learning. So I'll start talking about deep learning now. And this is the last method I'm going to review. So deep learning models, they're basically complicated neural networks. And it's deep learning is now the leading machine learning technique in many image classification, reinforcement learning, text generation, translation, audio, video analysis, prediction tasks, etc. So if you're enjoying Facebooks or your phones, you know, face detection stuff, you'd be able to identify different people in your photographs. If you've ever used a chatbot online at, you know, a bank or something, basically all of the sort of cutting edge techniques are use deep learning at the moment. Now, just to quickly cover neural networks, they're loosely inspired by biological neurons in our brains. They've been around since the 50s, but there was various issues that sort of stunted their development, but these have now been solved or reduced. So here's a simple drawing of a small neural network where you have a certain number of input nodes. This could be each pixel of an image, for instance, or something else. It could be, say, in a regression task, it could be your humidity, your temperature, etc. And you have these multiple layers of these different nodes, and finally an output. Now, each of these connections here between the nodes has a certain weight associated with it, so WI. So if we look at this node here, the first node in layer 2, the input to that node will be x1 times by the weight of this connection, plus x2 times the weight of this connection, x3 times the weight of this connection, and there's usually a bias term, which I won't get into. So that sum is then fed into a nonlinear, what's called an activation function within this node. And so you can see that if we vary these weight values, so the weight values of the parameters in neural networks, we would vary them, you can push the input to this function around this x value. So you can see that you can switch that node off or on. So, you know, if the x value is down here at -8, the node will be off. If it's up here at 8, it'll be on, and in between there's kind of a nonlinear gradient. So the power of neural networks comes from this massive interconnectivity, and that's also what what we believe is the power of the human brain too, is this massive interconnectivity with these sort of nonlinear activation functions. So that's how a neural network learns, is it varies these weight parameters so that appropriate nodes get switched on and produce it. Oh, this is back-propagation. I probably won't really go into this, but basically the difference between the y and y hat of the output from a neural network is called the error term, and that's back-propagated through the network to come up with all your gradients, do the gradient descent stuff. There's a whole heap of literature on this if you want to dig deeper. Now, the good thing about neural networks is they're universal function approximators, and that's been proven mathematically, and they can theoretically at least approximate any continuous function with a finite amount of nodes. That means take any function, theoretically at least, you should be able to get neural network that simulates that function. But training them is a different story, training them effectively. So that's where the real problem is with good ways of training neural networks. Now, they're particularly good at image classification, but they can be used for a whole host of other things, but they're particularly good at image stuff. So in this case, I'll just quickly show you an example where we develop a network which classifies handwritten images. The input is 28 by 28 pixel images, which we flatten out to give us 784 input features. So that's 784 input nodes here. And the output is 10 nodes, one for each possible digit. And the output is what's called a softmax activation function. And that gives basically a pseudo probability of each class for the input image. So, you know, it might be 10% chance that this image is written 1, 80% image is written 5, or something like that. Gives you sort of a probability of each classification. And I'm going to show you it's 3 by 50 node hidden layers. Let me just quickly go to the code here. There we go. Where are we? Okay, so this is what the images look like, handwritten images. So in this case, we've got a 5 and a 0. So we've got a whole heap of these images which we can input into our network and with the corresponding labels. Won't go through the code too much. Here we create a test training data set and a test data set. I'm not doing any hyperparameter stuff, so there's no validation data set. Then I create, here I'm using that TensorFlow package I mentioned earlier, which is used for deep learning, and so it makes it really easy to create neural networks. Basically, I create a model that flattens out the input images, and then we've got 3 hidden layers with 50 nodes in each, and then finally an output layer with softmax activation function. Hopefully this all works. All right, so now it's training. I don't think I'll wait for it to finish. Yeah, you can see there, so it's going through 10 epochs of X amount of iterations. And you can track how its loss is going, its accuracy as it's training. You can see the loss is reducing each epoch and the accuracy is getting higher. I won't wait for it to finish, but that's basically it training now. Now if I jump back, you can then examine how the losses behave. Sorry, let me just start this again. How the loss and the accuracy have behaved during training. So the orange line here is the training progress. You can see that the accuracy increases. The blue is the accuracy on the test data set as the training progresses. And you can see that what should always happen is that your training accuracy starts to become greater than your test accuracy. Converse with the loss. Now you can also with that softmax activation for the output layer, you can look at the probability of the image actually being a certain handwritten digit. So in this case, the prediction is 8. So it's predicting that this is actually an 8, and you can sort of see why. You know, it's actually a 3. So the image is actually labelled as a handwritten 3, but you can see that it kind of looks like an 8, right? And the probability of it being an 8 is it's actually quite confident that it's an 8. So it's got 84% probability that it's actually wrong. But you can see here that there is also a non-negligible probability here for it being a 3. Makes sense. And in this case, it's quite obvious that the handwritten digit is a 9. The prediction is a 9. It actually is a 9, and the probability is really high that it's a 9. Hopefully that makes sense. Now, deep learning. Deep learning is basically neural networks with lots of layers. So this is how this is how neural networks became so powerful. A number of factors presented networks from going really deep, but these have now been at least partly solved. I won't go into these details. You can look them up if you like. Called the vanishing gradient problem. Computing power is obviously pretty obvious. One big thing is they found out that graphical processing units, so GPUs, which are used, in gaming machines and all the rest, they're actually really good at performing the large matrix calculations that are required when you're doing neural network training. And so if you want to do deep learning, you really need access to some GPUs because they're hundreds of times faster than the calculations when they're performed on CPUs. And then finally, big data is really where deep learning models come into their own. So you can see here that the performance of older learning algorithms tends to plateau at a certain point, and you keep giving them more data, but they don't get any better. It's actually the opposite for deep learning. So that's why it's so powerful. In this day and age, when when we've got access to so much data, deep learning algorithms just keep getting better and better the more data you feed them. So that's why they're really starting to come of age, these algorithms. And you think of.
I was going to say on that, Andrew, is there like we're talking about overfitting before? Is there an equivalent risk of overfitting with neural networks if you make something overly complex, add lots of different variables, lots of layers for a fairly simple problem?
There's the risk, but the more data you give a deep learning algorithm, the less likely it is to overfit. So because say you've got some noise in a certain percentage of your data, if your model starts to go after that sort of characteristic of noise, but then you give it more and more data to train, that's not going to be the same characteristic, if you know what I mean. So it's going to change because it's all random. You know what I mean. So
yeah.
So it'll learn to generalize better the more data you have.
Yeah.
There's also certain architectures in deep learning. One of them is called ResNet, where it can learn to basically, it can learn to, what's the word, decomplexify itself. So it'll switch off layers basically that it doesn't need. It can learn that. So yeah. It's its own complexity. If that makes sense.
Thanks for that.
No worries. So I'm almost done. Hopefully this hasn't been too much of a brain strain or boring. So in this case here, I'm showing this is a 34-layer ResNet network. So you can see this is a true deep neural network, 34 layers. The ResNet architecture, that's the one I was saying that can determine its own complexity, if you like. They've created ResNet models that are hundreds of layers deep. So but to actually train that sort of model, you need lots of GPUs and significant amounts of computing hardware. But that's where state of the art is on these really deep neural networks. There's lots of different deep learning architectures. There's convolutional neural networks, which is graded images. There's recurrent neural networks, which can model time-dependent or sequential relationships. So text, speech, video. You could also use it for load forecasting, that type of stuff. There's new architectures coming along all the time, various combinations of the above and so forth. There's heaps of research going into deep learning. This is really where all the researchers, well, not all of it, but the vast majority of research is going into deep learning algorithms. The problem with deep learning is you've got to be sensible with it. It's a super powerful method, but if you're trying to use it on a simple problem, you're probably going to overfit and do something. So don't be like this guy. And finally, just to cap this off, reinforcement learning, as I was saying before, you're training an agent to interact with an environment. The agent's brain can be a neural network. Usually it's a deep learning model. So the agent's brain, if you like, is a deep learning model. It performs actions in an environment, and then the environment feeds back what state that agent is in and any reward it's got for doing that action. And so the idea is that the agent becomes smarter and smarter, if you like, and it gets more and more rewards. So the obvious thing there is video games, Space Invaders or something like that. That's where a lot of these algorithms are trained. But you can also, as I was saying before, you can basically take any task and make it into a game. So I've been experimenting using reinforcement learning to make good planning decisions. So, and in that case, your reward is kind of the inverse of your risk or the inverse of your cost, that type of thing. Anyway, so this is just some stuff about EQL, some existing uses and new ideas for the use of machine learning in EQL. So existing uses is they're experimenting with some pole top condition assessments using imagery. So using deep learning networks for image segmentation and diagnosing pole top condition problems. It's being used for short-term substation and feeder forecasts using various regression and clustering methods. We're also using it now to, someone in the forecasting group is using it now to detect when there's what the true reverse power flow is on feeders which don't have kilowatt readings, they've just got amps. So just using the pattern of the amps in the middle of the day, the shape of it, to estimate what the reverse power flow is for those feeders. Some work I'm doing on demographic and land use based strategic load forecasting. And then, as I said, risk optimized investment decisions, something I'm working on. And then we've also used clustering to segment regional feeder types to generate representative feeders. Anyway, I think that'll do me. There's some new ideas there I'll just leave on screen, but these are just brain dumps and no feasibility testing, but where it could be used in the power systems type area. Well, there's many more. But yeah, I'll stop talking now, and if there's any questions, fire away.
Thanks very much for that, Andrew. Yeah, really, really interesting presentation. A lot to take in there. I've probably asked my share of questions for the time being. I'll throw it open to anyone, either on the line or I think we might have got one or two questions through the chat. Is there anyone online?
There was one that came through on the chat, which I think Andrew's done an excellent job of answering already in just those last two slides. However, I might expand on it a little bit, and given we've got people online that don't necessarily work in distribution network service provider or for EQL, Andrew, from your perspective, what are the real opportunities for machine learning, I guess, more broadly in the power industry, and some use cases you think that would really stack up to use machine learning in?
Oh, good question.
Put you on the spot.
Yeah. I think all types of load forecasting, I think there's real opportunities there to improve our load forecasting systems.
What about financial side of things?
Yeah, there is. Yeah, so there is work going on, and I'm not across it. I've just heard about it. There's work going on about the retail business. What are they doing? Basically, there's I'm showing my ignorance here of how retailing and retail works and all the, pill prices and all that type of thing. But they are using it to predict bill prices and what have you, to do risk hedging and all that type of thing. I don't really know what's going on, but I know they are using machine learning algorithms. I know one guy is using a machine learning method called support vector machines to do that. So yeah, there's that side of things. There's various companies out there looking to use machine learning to become rich off the stock market. I don't know how successful they're going to be, but so that would, I guess, extend to things like the market as well.
Yeah, so I guess you've referenced a couple of things there around forecasting. Would you say forecasting using existing data sets is a real strong use case for machine learning?
Yeah, I would think so. The other thing is, this might be a little controversial, but I see a future where you could perhaps create like virtual planners using that sort of reinforcement learning methods, which being a planner doesn't sit that well with me, but but yeah, you could sort of imagine a future where that is possible. There's also stuff like fault condition assessment and forecasting of plant failures and that type of thing based on various condition monitoring data. It's possible as well, I think. So
with that, Andrew, on some of those problems, some of the examples we talked through come from applications where it's fairly easy to classify what's right and what's wrong, or what's good and what's bad. Like, for example, the numbers and image processing or letters, it's fairly easy to say, well, this is an A, this is a number one. But for more complex problems, like what's an optimal planning decision, where there's many, many different factors that would determine it, how do you come up with ultimately this is right or wrong, or this is what the answer should have been?
Yeah, the only way you could do it is compare it against. The only thing you could possibly say is that it could be better than what humans are doing. So, like if a certain planner would make a certain decision based on their experience, and you can show that this algorithm would reliably produce a more efficient set of solutions, and you could measure that based on cost or risk or whatever, then that would be your benchmark, if you like, in those cases, I would imagine. Does that answer what your question was?
Yeah, sort of. So I guess it would take a bit of, like, I guess, how do you take some things which can be at times quite subjective and make them objective, like risk assessments and things like that, and measures of risk can be sometimes subjective.
Yeah,
but I guess,
I'd be in favor. I'm in favor of making risk assessments less subjective. Another discussion, I suppose.
Yeah. Just as a step back question, I mean, you really did walk us through quite a big gamut of machine learning. Oh, sorry, I accidentally muted myself. Walk through from the fairly basic to getting into some quite heavy stuff with deep learning. Is there any resources that you'd recommend for people that are starting to play in this space and maybe looking to dip their toes in the water?
Yeah, I mean, there's a whole heap of online stuff. You wouldn't want to jump in straight into deep learning, but just basic neural networks and some of the more basic machine learning techniques. There's so much material. There's textbooks. There's online. Yeah, there's so many tutorials, and there's a lot of sample data sets out there that you can play around with. That type of thing. So, yeah.
I heard there's a good blog somewhere.
Is that where you're angling? Well, if you're interested in deep learning, my blog, Adventures in Machine Learning, that covers deep learning using TensorFlow mostly. Yeah, if you're interested in that, check it out. But yeah, if you're starting out, perhaps deep learning isn't the way to start. But yeah, I mean, what's out there?
Appreciate it, Andrew.
No worries.
Did just have one more question come through on the chat. How successful has machine learning been for pole top condition and defect assessments?
My understanding, so I'm not on this project, but my understanding is it's still reasonably early days, but they are having success. Having success in segmenting the images, so identifying this is a pole, this is a cross arm, this is a conductor, and so forth. And they're having some initial successes in identifying obvious defects. I think the biggest problem is having the data where the human-generated supervised data, if that makes sense. So, you know, someone who's gone through and actually confirmed that, yes, this is a defect. Like, I think they're having trouble generating those large amounts of data that's required, labeled data, if that makes sense. So, you know, this is definitely a cross-arm with a problem. This is a cross-arm with no problem, so on. I think that's my understanding where they're up to, but there's still work to be done in that area.
Thanks for that, Andrew. I haven't got any more questions on the chat, but I open it up to anyone who's still on the call and wants to ask a question.
All right, guys, we might take silence, given that we are getting close towards the 2:30 finish time. I will throw you to questions one more time before we close out, but I just wanted to say, look, thanks very much to Andrew Thomas. He's taken time out of his day to come and present here. So really, really do appreciate that, Andrew. Very, very informative and interesting presentation. And look, if anything, hopefully has built a base level of understanding and sparked a bit of interest in this space and a bit more understanding, because I think, as you said and sort of started it off with, machine learning and this artificial intelligence does have a lot of hype about it, a lot of mystique, and it's really good to get to peel back those layers and see what's actually behind the curtains of it from someone that has a lot of knowledge in this space, and see, for some of the stuff that really, you know, at one extreme is relatively simple decision trees, that sort of stuff, but at the other extreme is really complex, unexplained, you know, unknown networks. So really do appreciate that. Look, I'll throw to any potential questions one last time. Is there anyone with any questions? All right, well, guys, we'll call it there. Thank you very much for those dialing in on the call, and thanks again, Andrew. Really appreciate your time.
Thanks, everyone.
Cheers, guys. Just a quick throw also to those Brisbane located people, a reminder that it's the 20th for the networking event and 21st for the annual technical committee meeting. If you're interested, get in touch for the networking event. That's unfortunately not on our CIGRE events page at the moment, but should have been an email to NGN members. The technical committee meeting is advertised and you can register through CIGRE Australia's event page. So, all right, thanks very much, everyone. Really appreciate you joining and dialing in for the conference today.
Thanks for hosting, Matt.